Hello guys, it's the Caribbean Bookworm, and in this video I wanted to take a little bit of an interesting dive into a very interesting aspect of classical physics, which actually turns out to be very useful in even areas of modern physics, such as especially particle physics, and that is the conservation of momentum. So without further ado, let's jump into it. First and foremost, if you're new to this channel, welcome to this channel. This is basically a channel in which you can feel at home, especially if you're interested in science, books, and anything of the like. Feel free to go through my channel, check out some of my older videos. If they pique your curiosity, then hit the subscribe button, like my videos, as these greatly help to reach enthusiastic viewers such as yourself. Now let's jump into the concept of conservation of momentum. Now when you think of momentum, you might have different pictures in your mind. You might have the throwing of a basketball, the moving of a car, the moving of a plane, or anything basically that incorporates a little bit of motion. And you'd basically be right. As long as something such as a massive body carries some sort of velocity, then the thing most definitely has some momentum. And one very straightforward but useful way of thinking about this is what's usually done in physics textbook, and that is using the example of two billiard balls basically laying on a one-dimensional track, you could say. You have one ball which is moving and going to collide with a stationary ball, kind of transferring a little bit of its kinetic energy to the other ball, and you need to see what type of collision is happening, and a lot of this can be definitely figured out due to the conservation of momentum. This conservation of momentum entails that the momentum basically that this scenario has initially must be conserved, so it must prevail at the end stage as well, whatever that end stage might look like. So the end stage might have different outcomes, such as, for example, if the one ball is going to knock into that stationary ball, well, it might transfer all of its kinetic energy to it, in which case basically what you would have is that this ball is moving and then knocks the other one, and the other one starts moving with the same velocity, while this one stands completely still because it transferred all of its kinetic energy to that other ball. That is a form of what is known as an elastic collision. You also have something known as an inelastic collision, in which basically, well, the kinetic energy is not fully transferred from one object to the other. So in this case, if you have the ball going and knocking the other ball basically, then that first ball is still going to definitely move, but very likely a little bit slower because it lost a little bit of its momentum for sure, and it's also experiencing some friction from the table as well. So from this you can very likely guess that most cases you have inelastic collisions, but basically you have that the kinetic energy from that initial ball that it was moving was not fully transferred to that stationary ball, which was, well, not moving. You can also have, if the two balls are going to be knocked towards each other, then instead of them fully sticking together, they might bounce a little bit off of each other, or even if they do stick together, they might still be moving a little bit, as there's still a little bit of kinetic energy that's kind of leaking outwards. So these two forms of collisions are definitely examples which you might have seen from classical mechanics, especially with the analogy of billiard balls, which I think is very useful of thinking about this, because as I said before, even in the cases of particle physics, you can still somewhat loosely think of particle interactions as being just bunch of billiard balls doing things. As a matter of fact, one of the core concepts of Einstein's theory of relativity, in particular the special theory of relativity, is a relationship between energy and momentum basically established by this equation right here. This equation, well, if the momentum is negligible, say if something experiences no momentum, then it boils down to the famous E equals mc squared equation, which is much more popular out there. But this, what you've just seen, is basically the full expression of, well, that equation basically. So with this equation, with knowing the energy which you have for a given system, you can actually tackle some very interesting particle physics problem without even having to necessarily take a deep dive into quantum mechanics. Well, unless you want to get into the nitty-gritty details. But to get a general overview, for example, in particle colliders, accelerators, you can have basically that these particle accelerators, especially the more old-fashioned ones, are basically accelerating a proton, for example, letting it approach very high velocities, relativistic velocities actually, so velocities that are very close to the speed of light, and have it hit basically a fixed particle. So this fixed particle could be another proton. And when this happens, basically you have that the particle that just went around a couple of times very, very fast is going to meet that fixed particle, and basically it's going to have a heck ton of kinetic energy since it was moving so fast. What you will get is basically a very interesting type of collision event from which you can have actually neoparticles, because protons themselves are what are known as hadrons. They are, you could say, heavier particles that actually consist out of much smaller fundamental particles, such as the different quarks which are within these things. And sometimes a problem which particle physicists typically face, especially in this scenario in which you have a proton moving and trying to hit a fixed target, what you might have is that what would be, for example, the minimum kinetic energy that that proton traveling would need in order for this collision to produce a particular particle of interest. So say if they're interested in producing, say, a pion or any other exotic fundamental particle or particle pair or anything along those lines, then you would need a particular threshold energy, you could say, from that proton that's moving, such that when it hits that targeted, like that fixed particle, you get the desired particle that you're interested in. And to get these desired particles, you want there to be a threshold energy which is bigger, which is at least bigger than the rest energy of the particle you're interested in. So if it's a pion, you want the threshold energy to be at least bigger than that, you could say, that pion. And this lies at the core of why basically particle physicists try to smack particles together, because in the smacking of particles, because for example in the case that they smack basically like protons together, because they consist out of smaller particles, then you can get this particle shower, you could say, or this jet basically, which basically consists of many different fundamental particles. And the higher the energies you can reach with this, the more exotic particles you can get from these collisions. Hence why another way in which especially most modern particle colliders go about this is by not having a proton, for example, going about and smashing into a fixed target like particle, but having both particles basically moving but in opposite direction basically until they basically meet each other, in which you have a tremendous release of energy, and of course with a tremendous like energy release comes a tremendous amount of fundamental particles which could be discovered. This is how a lot of fundamental particles were discovered, especially in the late 20th century, like in the 1960s onwards. This is how people came to know about a bunch of different quarks with a bunch of funny names which you might have seen online. And even, for example, the discovery of the Higgs boson was done in pretty much this manner, by smashing particles and trying to find the energies which theorists predicted the Higgs boson to be in. Now, besides these interesting applications of, well, using Einstein's special theory of relativity in particle physics, there's also an application which I personally find very interesting, where this concept of actually conservation of momentum still comes into play. In the case of particle accelerators, you saw how basically the scenario at which you have a particle hitting a fixed target is pretty much like that billiard ball hitting the other billiard ball and you getting like an inelastic collision event. You also have something very similar with these fundamental particles known as neutrinos. Neutrinos are often of major interest, especially in areas like modern high-energy astrophysics, which, if you think about it, with astrophysics, that's pretty much the complete opposite end compared to something like particle physics, which is interested in fundamental particles and their various interactions. With astrophysics, you're, well, pretty much interested in astrophysical objects. You're interested in studying the physical processes which are responsible for the majority of astronomical objects out there that scientists can observe. neutrinos play a very important role, as these are things which are prevalent throughout the cosmos. They're small fundamental particles, particularly they're leptons, so they're I think they're half spin particles, if I'm not mistaken, and also they're neutral leptons, so they don't have a charge. And neutrinos basically they can go about their business throughout the cosmos, and because they only interact through the weak force and gravity, but their mass is so small that for a good period of time, physicists even thought that neutrinos might be massless, but that got proven wrong. But because of their very small mass, you can somewhat even disregard their interactions through gravity and mainly look at their interactions through the weak force. The weak force acts only through very small distances, very similar to the strong force. So that means basically that unless a neutrino passes very close by to something like the nucleus of an atom, like for example a proton or a neutron, then it's very likely to just go about its business and continue traveling whatever path and trajectory it was following in the first place. This is why a lot of neutrinos that pass through the Earth, and a lot of them come from the sun or from other cosmic sources, a lot of these neutrinos just pass through us. And at the moment, I forgot what the number exactly is, but there's like a billion something. I might put it down here, but there's a bunch of neutrinos passing through us every second, like while not interacting with us at all. And that is because the nature of atoms themselves, if you take a deep dive and zoom into the microscopic and atomic world, there's a lot of space actually between the nucleus and the electrons, which are kind of orbiting the atoms basically, which most things consist of. Because of such huge spaces, basically, there's a lot of ways which the neutrino can just zip by through an atom without even interacting like with anything. But if it does interact with something, then you get a very interesting process. You get something a lot of times what physicists model as deep inelastic scattering. And deep inelastic scattering is a very fancy word, but it's basically saying that when these neutrinos go by through very close to the nucleus of an atom, basically they can interact with, say, a proton or a neutron, and via the transmission of a virtual particle or a boson, such as the W plus boson, the W minus boson, or the Z0 boson, you can have them doing something with that particle in such a way which basically they knock off either the neutron or the proton from the nucleus and kind of transmuting that atom. That atom turns into something else, and basically you can have, in a very indirect manner, you can kind of detect that a neutrino has just passed, basically by the interaction of the neutrino with an atom. And when that atom changes, maybe some energy is released, or implicitly some energy is released through something else happening, like the change in the atom causing a chain reaction which maybe releases photons, which you can then detect using like your detectors. This is of course a very hand-wavy explanation of it, as of course I personally have not dived too deep into particle physics yet, but this is just a very general understanding, and I encourage you to look up some literature on this topic as it's super fascinating. You can pick up a book like Astroparticle Physics by Grubin, I think, and you can dive deeper into this concept. But regardless of that, you can see how basically this concept of elastic scattering and inelastic scattering, which basically boiled from things like billiard balls hitting each other, is used even in studying things like particle interactions in particle physics, or in studying how neutrinos, which also has to do with particle physics, but how you can detect neutrinos from cosmic sources by, again, using these models of collisions, basically. It is a super fascinating concept, and is why I think this idea of conservation of momentum is so underrated, because even though it is a concept that is primarily introduced in things like classical mechanics or courses like classical mechanics, it has such high values and is prevalent throughout so many aspects of physics. I hope you found this video entertaining, interesting, and if you did, feel free to leave a comment down below and let me know what you thought of it and whether or not you have been thinking about this concept yourself as well. I hope you found it again interesting, and I hope to see you guys very soon. Bye.